Starting with blood, when we first look at it, we're going to look at the components of blood, we're going to look at the functions, we're going to look at the different cell types, the red blood cells, the white blood cell types. Then platelets, they go together with blood clotting. We'll look at that. Then we go into the plasma, which is the non-cellular components. And then, of course, the big deal about the blood is oxygen transport, that carbon dioxide transport, so we'll talk about that. And then we end up with discussing blood groups. Blood is a fluid transportation tissue. It's a connective tissue. We thinking back at connective tissue, the key there is connective tissue has cellular components and has acellular components. Like bone is connective tissue. And blood is also connective tissue. And you go like, how can that be? The reason why is it's got all these components. And embryologically comes from a similar place. So in blood cells, the cellular components, the cells themselves, are either red blood cells, white blood cells, or platelets. Then besides the cells in blood, if you think blood is flowing around, you have two more things. You have an extracellular matrix, you have a blood plasma, and that's the watery stuff. In a bone, that will be the calcium. So it's totally different. Here it's basically water, there is basically hard bricks, but it's the same component. So that's why it feeds back into the same type of tissue, the connective tissue. And then the other thing that connective tissue always has is fiber. And in blood, we have soluble fiber. And that means that fiber is just, it's like Metamucil when you swoosh it up, you're drinking fiber, but you don't even see it. You're just drinking it, it's dissolved. It's the same side of thing, it's soluble. So it's not precipitating out, so it's not separating itself from the fluid, the liquid. And that's a very interesting process. We're going to get to that later on in this chapter. That has to do with clotting, blood clotting. Blood clotting is when you cut yourself, how is it going to close out those vessels that spew out blood? How do they close? That's where that comes into play. So it's a very interesting thing. When we look at blood volume, it's about 8% of the body weight. And a person of 70 kilos approximately is about 5.6 liters, or these kind of things together, put together. So you can make cake. There's a gallon, there's a quart, there's a pint, and then there's something else. It's about 5.6 liters, just to visualize it. The cellular components of blood, so all those cells, the white blood cells, the red blood cells, the platelets, they're all made in the red bone marrow. And the red bone marrow is at the ends of bones and on some of the inside. So very specific areas of bones are making the blood cells, the components. So when you think making red blood cells, making white blood cells, you always think bone, red bone marrow. The term hematocrit is important, and that's the term that is the total blood cells. The blood cells expressed as a percentage of the total blood volume is called hematocrit. This is important in part because we got this fluid floating around in the body, and not all of it is watery. Some of it is cellular. We don't want the hematocrit to be too high because then the blood gets more sticky. There's more blood, more cells in it. So it's important to know that value. And the definition is right there. Hematocrit, the blood cells expressed as a percentage of the total blood volume. We look at the function of blood. Well, red blood cells, as we know, probably already by now, their big deal is they transport oxygen. So the red blood cells transport oxygen from the lungs to the tissue, and then carbon dioxide back to the lungs. So in the lungs, oxygen fills up, the oxygen goes into the red blood cells, and then in the body tissues, the oxygen goes into the tissue, and then the cells, when they have oxygen ready, they can take glucose or other food sources and make energy out of that. So the oxygen is used to make that ATP. So that's important. Then white blood cells defend us against pathogens in foreign bodies, so they are part of the immune system, so the defensive system. And then also, we have many substances that are dissolved in the plasma, and they're transported through the body. So the body is kind of like a freeway system. So we got nutrients, we also got metabolic wastes, we got hormones. All that stuff can travel around in the blood. Then further, we just briefly mentioned that fiber thing. When that insoluble fiber becomes soluble, it can patch a cut in a blood vessel. So that's when that's happening. And so that's blood coagulation. So when a vessel is broken, we need to repair it. So as one part of that is the blood vessel that feeds blood into the area that is broken shrinks together a little bit, so it doesn't have so much blood coming in. But then little platelets start collecting because everything slows down a little bit, and when the slowdown of the blood happens, the fibrinogen, that soluble fiber becomes insoluble, and it's like little threads that we can patch up that hole. So that's kind of cool. It's very, very delicate. So the big deal there is the fibrinogen that I mentioned over here. Whoa, one back. That fibrinogen, that soluble fiber. Remember, we used that term GEN as a not quite mature, from Genesis, the creation. This is one of those places where we have a not quite finished product in a fibrinogen that's a soluble fiber, and when we need it for its action, then we make it into an insoluble fiber, and that name for that then is fibrin. We just cut away the OGN. We'll get to that slide, but that's a really cool thing. It's also a very, very delicate thing, because if you get some of these clumpy stuff together and it breaks off and goes through the bloodstream, you might get a stroke. That's part of that process. Then another thing in the function department for blood, heat. Heat's produced by the internal organs and is carried to the body surface via the blood. So the blood can transport heat around in the body. If it's really cold, it can shrink the blood vessels on the surface and conserve the heat on the inside. If it's really hot outside, you can get all ready and fluff, and then the blood vessels get to the surface and they radiate the heat off the body. So that's kind of neat. Let's see, that's good for function. Now let's go to the red blood cells, the erythrocytes, if you want to use the technical terminology. Erythrocyte. A microliter is like nothing. It's like a millimeter by a millimeter by a millimeter. It's a cube, very small cube. Don't allow it in Las Vegas. So the microliter contains about 4.5 to 5.5 million red blood cells. So that's a lot of cells all in one little cube. Those things are round, they're disc shaped, they're concave. That means they're looking like a frisbee on both sides. So it goes in, bend in on both sides. That's concave. Remember that? Cave, you go into a cave terminology, as in concave. And this is optimal surface. Oh, this is why they're concave. In part, well, they are concave because the nucleus is not there. There's no nucleus. These are anucleated cells. So the nucleus was popped out, and therefore it's a vacuum in the middle, so it shrinks together like that, like this. But that makes it a great surface to volume ratio, which means the surface is all around the thing, and the volume is once on each side. So with this, the diffusion distance is the same to pretty much anywhere from the cell from its surface. And so when we want to bring oxygen in, oxygen is like diffusion, it just goes right in. It's like a magnet. The magnet wants the oxygen, and the magnets are in here. The hemoglobins are like magnets. If they're lacking oxygen, they suck it in from the atmosphere in the lungs, in the alveoli of the lungs. But so since all the distances from the surface to the inside is a certain amount of distance, it's not like you have a round cell and at some point some oxygen has to travel all the way to the inside. That's way too far. Couldn't do that. So they call that optimal surface to volume ratio. We have that too. If you make us too tall or too short, it's not going to work. Look at the short people. It's really hard. Like the short people, it's hard for them to ambulate. They don't walk the same way we do. Or then you look at the people who suffer from gigantism. 8 feet tall something. It's not easy for them to live. They get crushed under gravity in a different form. So we also have that as an organism, but cells also have that. And so inside this bag is basically hemoglobin. And so it basically becomes a bag of hemoglobin. And hemoglobin's claim to fame is really basically that it binds oxygen to oxygen reversibly. So it can pick up oxygen when it's void of it, and it can let it go when it's got plenty on the other side, like the tissue needs it. So in the lungs, it's going to pick up some oxygens, and in the tissues, it's going to let go of some oxygens. And then the oxygen is used to make ATP. Oxygen-rich blood appears bright red, and oxygen-poor blood is darker red. That's where the idea of that blue and red blood vessels come from. It's the oxygen for them. The other reason why this shape is cool, it's good in passive deformation, and those little things can squeeze through blood vessels and narrow passageways easily. So that's cool. So when we look at how many of these little things we have, these RBCs in 1 little cubic millimeter, and we also know these things only live about 3 months, and then they have to be discarded. So we got to make a lot of them. So the need for red blood cells is determined by the tissue needs of oxygen. So there's a negative feedback sort of thing. More oxygen needed in the tissues. RBC production go up, and who says it's going up? It's the renal hormone erythropoietin. Oh boy. Erythrocyte is an RBC. Erythropoietin is a hormone that tells the body to make more. Renal refers to kidney. Whenever you see renal, you're thinking kidney. This, though, the kidneys have to do with red blood cell production, has to do then why dialysis patients often become anemic, because their kidney function is impeded. If we have an increased number of cells, red blood cells here, for example, that's called polycythemia. Poly means many. Cythemia means cells. So too little is an anemia. Too many is polycythemia. Red blood cells, red blood cells. Oh, and here you just see the flow chart. Low oxygen, this is a new one, I think. Low blood oxygen goes to the liver and the kidneys. The liver can do that too. Erythropoietin goes, but the kidney's the main one. Erythropoietin goes out, we make more blood cells in the red bone marrow, and that's the negative feedback. Then erythropoietin goes away when we have enough RBCs to feed the oxygen needed in the tissues. That's why training people go to Colorado to train, and then they compete at sea level. So they go up to, I don't know, 6,000 feet or something to train, because up there oxygen concentration in the air is less. There is more need for oxygen. The body's going to make more RBCs over time. And then they come down here to compete. They have more oxygen carrying capacity, means more energy. Haha. I know, it's a trick. If you do it naturally, you can do it. Some people, what they do is they inject red blood cells before they compete, but that's very dangerous, I would think. I wouldn't do that. Lifespan of an RBC is about 3 months, 120 days. They come from stem cells in the red bone marrow at a rate of about 160 million a minute. So that's why you can fit so many in a small little space. They're broken down by the liver and the spleen. The iron is sent back to the bone marrow for recycling. That's cool. And then another portion is used in bile salts. And bile salts is the gallbladder stuff. They are used to emulsify digestive fat droplets to prevent them from aggregating, which makes them impossible to absorb from the small intestine into the bloodstream. So what happens is you got a salad dressing. You put vinegar, you put oil in, and then you got to shake it. And as soon as you stop shaking it, all the oil goes together, all the vinegar goes together. The oil wants to get together and aggregate. Aggregating means clumping together. What we need is we need a molecule like soap. If you wash your dishes, you take soap, the greasy goes away. Bile salts do exactly that. The soap emulsifies the fat. That means the soap in itself, or the bile salts here, what they actually do is they have a polar region and a non-polar region. It's back to the similar like the phospholipid bilayer, the cell membrane. So if they have a part of that molecules that are in there, a bile salt, that is polar, negative, positive, and the other one is non-polar, you can bind and go in between these aggregated cells and make smaller droplets from the big droplets. That's what emulsification means. And so we need that because when we eat fat, if it all clumps together in here, it's not going to go nowhere. And the blood, we need a lot of fat. The brain is 80% fat, so we need a lot of fat in our diet. And so, as a byproduct from the red blood cell breakdown, we can use that. Now, that's pretty cool. Yeah, the body's pretty sharp that way. I like it. So when you look at your slidey things here, all the red ones are red blood cells. Because that's going to be on the test, that thing. And you have to identify all the little cells. So after the red blood cells, the erythrocytes, we get to the leukocytes, the white blood cells. So the word leukocytes means white blood cells. We don't have millions, we have thousands in a microliter. We have 5 types of them. We have, and they group them depending on their staining qualities under the microscope. Don't worry, we're not going to get a microscope. We'll have them like that. I prefer that. We have granulocytes and we have agranulocytes. So the granulocytes, when you look at the slidey things, I'm sorry I took yours, but when you look at, these are all white blood cells. All these weird things are white blood cells. Everything that's round other than the red blood cells are white blood cells. And some of them in the background have little bumps, little granules. Those are the granulocytes. And then there is others that are smooth in the background, and those are the agranulocytes, because the word A just negates what the word afterwards is. So they group them by how they look. That's pretty important because that's pretty superficial to me, but that's what they did. So if you have a stain thing, there's 2 types. There's the one that these backgrounds have been scratched off and make them pink, and there's the ones that's not happened. Make sure we talk about that when I come to the table doing the lab, because there's new plates and old plates, and they're looking a little bit different. So when we look at the granulocytes, we got 3 types. We got neutrophils, eosinophils, and basophils. I like this slide a lot, by the way. because it tells you everything you need to know, I think. So when I look at this, the neutrophils, the back droplets in terms of identifying, they're stained neutrally. So on your slide thing, just you have bumps, but you don't see the difference in color between the background and the bumps. Because then you got the eosinophils, and those have back bumps that are red. They stain redder or orangey, but more neon lighty. That's why it's eosinophils. And then the basophils, those stain blue. They're like basic, not acidic.
Which one are
The eosinophils are red, the neutrophils are neutral for neutrophil, and the basophils are blue. And then you've got some descriptors down here in the booklet. I like those, but you don't have to look at them, from my end. There's enough identifiers to figure it out. All right, let's go back. Yeah, let's do a little bit something general before we go into the different groups more. When we have an increase in white blood cells, what would that mean? You're sick, right? Yeah. So if you get your lymph nodes, you feel them back here, that's an increase. When they're swollen, they're filled with white blood cells to help you. So when we have more than 10,000, remember it was 4 to 8 or something? More than 10,000 a microliter, we're having an infection. So that's leukocytosis. Leukopenia, the word penia means not enough, little. So that's when we don't have enough, when we diminish below 2,000, and that usually means damage in the side of the formation, which is due to certain drugs or cancer. That would be leukemia. But corticosteroids can do that too. So when I have 30-year-old people walking around and telling me they get cortisone shots, that's what that is over time. I want to keep that for when I'm 70. When it really hurts when I walk. Not just like my knee hurts, and I really hate when my knee hurts because I'm too important for that knee to hurt. That damn freaking knee. That's the patient that goes back out, and I say, go down the street and get some ibuprofen. Because you can't talk to your body like that. You have to be honoring of your body. Except for the lymphocytes, the white blood cells and the red blood cells both are made and mature in the red bone marrow. So there's one type that will not do that. There's one type, they're called lymphocytes. Those are your B cells and your T cells. Remember B cells and T cells? Anybody not remember B cell, T cell? 8? Anybody remember 8? Good. Yeah, in 8, the T cells are down. The T helpers are down. So that means the 8 messes up these cells. And that's partly why it's so bad. But those are very specific. Those are made in the red bone marrow. And then they go to the thymus here in the front and some other lymphoid organs. And they mature there and they learn how to do their work right. But everybody else gets that done in the red bone marrow. And I think that's the important point here. When you think of blood cells making, you're thinking of red bone marrow. White blood cells are really cool because they actually start in the blood. They use the blood to get them somewhere, but then they crawl around in the body. They're like amoebas. They move. They have actually, they move to the site of activity. And mostly that's outside of the vascular system. So they can go there, they have signals. If I cut myself here, there's signals that are sent through the body that these white blood cells want to go to where I am, want to go to where the action is. And that system, that signal sending and then them reacting to it, that's known as chemotaxis. I call it a taxi with a chemical. It's a self-driving machine. And then the other thing is that white blood cells, when they move around, they can do that independently or autonomously. And that motion, when they do that, is called amoeboid motions. So that's a term that's interesting. And the last one in here that I put up as important, amoeboid motions, is this word called diapedesis. And that means when a white blood cell squeezes through a blood vessel, it goes through, it's called diapedesis, because pedesis means walking, pedestrian. Pedal means down here, that's foot. And dia means through. And so diapedesis literally means they're walking through the cell wall. And blood vessel wall, not the cell wall, the blood vessel wall. So that's how they get to their action. And then let's go briefly through what they do in terms of their action. So the granulocytes have these granules. They're mostly lysosomal enzymes. Remember, lysosome is destructive, killing. Lyse means killing. Autolysis is when a cell kills itself. So what they do in those inclusions, in those lysosomal enzymes, that those break down whatever comes at them. Neutrophils are the big ones that phagocytose. And phagocytosis means ingestion of foreign material, which is often a pathogen, destroying that by releasing lysosomal enzymes at it. That's like hydrogen peroxide. Think in hydrogen peroxide. And then often what they do is they perish themselves, and when you feel pus, you know they died for you. And you have no right to feel depressed anymore. Damn, I caught myself. Damn, blister, why is it hurting? So it's like you got some selfless critter in there, do their justice and be nice to them. So the next time somebody says, "Ooh, that's pus," it's just like, yeah, they did. They all died for you. Isn't that nice? They're the most numerous white blood cells. The first one that show up at inflammation, and they are the main part of what we then later call the non-specific immunity. Like if you get a pathogen coming at you, remember the first thing you do is you don't let the bad stuff come into the body. I mean, that's number one, right? And once it's in the body, you cut yourself, the skin's cut, that first line is the skin. It goes through in the skin. Then what are we going to do about it? We're going to send those guys over and say, like, just clean up the mess. That's called non-specific immunity. They're not like going like, oh, the chicken pox, it's right there. Let me get the chicken pox wiped out. Then you have one cell that knows how to wipe out the chicken pox. These just know how to clean up. They go in, they eat up stuff, they perish, as many of them, it doesn't matter. They're soldiers, foot soldiers. So that's non-specific immunity. We'll get to that. They're big at that. Then the eosinophils, phagocytosis, they eat an antigen-antibody complex and then bond to excess histamine and limit an allergic reaction. Good. What do? They limit an allergic reaction. We like that. So you're sneezing too much, you want more eosinophils. But they have to go to an antigen-antibody complex. When you look at a pathogen, you see a bacteria that makes you sick. There's going to be a portion of that bacterial wall on the outside that is representing of that bacterium that we can recognize that on, that the body can recognize that on. That part, we call it antigen. And then the body, when we get to making, recognizing things that make us sick, or the body doesn't like to tolerate it, makes these antibodies against it. And when they combine, we already know an antibody from our own body connects to a sickening thing. That's when then the eosinophils react and can scoop up excessive histamine, or the second thing they do is they attack parasitic worms, which is also helpful. So those stay in reddish. We'll get more to the antigen antibody complex when we get to the immune system. I know I didn't do a good job with that, but that'll come up. The basophils are the ones that release the histamine and heparin, and that's hypersensitivity reactions. So when you start sneezing and all that, then you say, damn basophil. They stain bluish. So they can overreact a little bit. I mean, the immune system is a very delicate process. We have a lot of overreactions, hypersensitivity reactions, especially with all the plastics, I'm sure, in our system at this point, and all the environmental toxins and all the stuff that comes at us. Just drink a lot of water. From there, then, so we did. Let me recap. We did the neutrophils, eosinophils, and the basophils. Those are the granulocytes. Now let's go to the agranulocytes, and we got there two types. We got the lymphocytes. Let's do those first. The lymphocytes on the plaque are easy to recognize. They're the one with the blue marble background. They're actually tiny when they are in the bloodstream, but they get really big in the tissues when they're outside in the tissues. They are the cells of the specific immunity. They are B cells and T cells. You probably heard those terms more. What's important here with the terminology is you've got to differentiate between leukocytes, oops, that's white blood cell, and lymphocyte, and that's B cell and T cells. T cells are involved in immune response that is cell mediated, so that's where the T helper cells come in that AIDS thing, that they don't work right anymore because T helper cells recognize something that we've already encountered and they help coordinate that immune response because we have T killer cells and they're like the sharpshooters standing up there and they kill everything that they're supposed to kill. Well, we want to make sure the right stuff and not the wrong stuff. And then we have these T suppressor cells. We're actually going to get to them soon too. And they also help suppress the immune response when it's too much or when it's over. So there's a lot of going on right here. That was these T cells. And then we got the B cells. And the B cells are the ones that make antibodies. So in order to get what we had in that previous slide, an antibody-antigen complex, we have to have made the antibody, so we have to have the pathology encountered previously and learned about it. And so that's why they call that specific immunity, or also they call it learned immunity. That's the same thing. So when you go to the doctor and you get a shot, you get a virus a virus that's attenuated that supposedly triggers these cells to make antibodies without getting sick. So that's how we work with the system to make it, to adapt it to the environment. The system alone does that on itself. That's in the old days when you go with the neighbor's kids because you got chickenpox. Then you get sick, and then your body makes these own things. And so you rather have that sickness in a controlled fashion, like when the kid's young, as in chickenpox, versus when we get older, or the German measles, or worse, when we get older with the pregnancy and the German measles, that could be a problem. And so we expose the kids to get those diseases when it's okay for the body to take it. Now we have many more vaccines, so we give a lot more vaccines. And that can have positives and negatives. We don't know that. We just have to figure that out over time. But people who get shingles, that's considered part of the chickenpox virus as we get old. There is thoughts that if we get the shingles vaccine, we might not get, the chickenpox vaccine and not get the actual disease. The chickenpox is not in the spinal cord somewhere, and we not have a chance to get shingles because of that. But we don't know that. It's all too young. Give us 50 years, then we know. So that's the difference between that B cell and T cells a little bit. Fundamentally, they're both considered lymphocytes. And then the last ones we're looking at is the monocyte. And the monocyte is the one with the pink background in the old plate. And in the newer plates, they're spread around where there's no pinky scratched off backgrounds. They're just the biggest ones, I think. We can go with that. They're big. Monocytes. They're large. They have a kidney-shaped nucleus. They have many lysosomes in it. They look very pretty. They mostly live outside of the bloodstream as macrophages. And macro means what? Big or small? Big. So to me, these are the big eaters. They eat the big stuff. They phagocytize, which means eating, and destroy bacteria, fungi, parasites, as well as worn out and damaged cells. Then they do something really cool. They're gonna eat the bad stuff, digest it, realize that's some bad stuff. Then they take the identifying part of the pathogen, which is this antigen thing, and they present it on top of their cells with another little fragment that says, that's like the flag of the American flag or the Swiss flag, or so everybody has their own little imprinted self-recognition thing. We'll get to that, but they present that bad stuff with the good stuff and tell the other immune cells, I got something, you got to deal with this. Come here, destroy me, but deal with this. And when we do that, we call these cells antigen-presenting cells, or dendritic cells. That's why they have these little spiky things. Dendrites are little spiky things. And this cell then becomes the link between the immune system knowing something is just bad stuff and we gotta get rid of it and wash it out, or something that we have to encounter again maybe and we have to learn about it, and we can make then antibodies with it and prime the T cells and say, you know this one, you're gonna shoot them down. And so the monocyte or the macrophage in tissue become very important in that link of the immune system. So that's another, now you can understand how the immune system is so complicated. You've got all these factors. It's really complicated to teach too. This slide just puts all those cells together. We got the red blood cells, we got the platelets we'll talk about, we got all the white blood cells right here. Just so you kind of have an overarching piece. You don't have to fully understand this, but I think this information you got here gets you really far in the school of learning these things. And pictures are always worth 1,000 words, so we want to do as many pictures as we can. So that brings us to the last thing in terms of cells in the blood. And that's the platelets or thrombocytes. They're made in the red blood cells by a cell called a megakaryocyte, and then they're released into the bloodstream as little fragments, cell fragments. So on your plaque, all the blue little fragments are platelets. They're not real cells. They don't live long. What is it? I think 5 to 10 days, and then they're absorbed by the spleen, which cleans the blood, sort of. Their major role is blood clotting, coagulation. So let's do that real quick. When a blood vessel gets injured or gets cut, it can be life-threatening because we have blood loss. So what we do when we need to fix that blood vessel to close that hole, that's the idea. We have a cut in the blood vessel, blood will go out, we need to patch it so we don't have blood to leave the blood vessel. First thing we do is we slow down the bleeding. We do hemostasis. Hemo means blood, stasis means standing still. And we do that via constriction of the blood vessels. So we're just squeezing those blood vessels so there's not as much blood going through. The technical term for that is vasoconstriction. And then after that, the slowdown of the blood lets platelets, and the other term for platelets is thrombocytes. Platelets / thrombocytes. Then they're being deposited along the injured vessel wall as they stick together into one another. So when they slow down, they get stickier, they cling to one another, and they cling to the vessel walls, and they start patching up this cut. And we call that platelet aggregation. And then what they do is they make a platelet plug. And then the last step after that is blood coagulation. And this is the delicate process that gets this soluble fiber into an insoluble fiber, from fibrinogen to fibrin. And we got all these clotting factors, and so I didn't write all of it down, but just sort of the last steps. But it's like 13, 14 steps to this process. And the reason why it is because it's a very, very difficult and a challenge if it's unnecessarily done. It can kill people because you can have a stroke from it. You can have an embolus created. That's a free fragment that flows through the blood, and if it goes through a blood vessel that's too tiny, it's going to clog it, and that could be a stroke. So the steps that I led here is, you see the prothrombin, thrombin, and that's fine. We don't need to worry about that. But then the last step is this fibrinogen from a soluble fiber to fibrin, which is an insoluble fiber. And then that goes and traps more platelets, but also red blood cells to this, and really makes a good band-aid that no more blood is going to be going to leave. Once the blood vessel then is fixed, we're going to have to dissolve this clot because we don't want it to come off and float around in the bloodstream. And that process is known as fibrinolysis. And lysis is always, you know, that breaking down thing, killing thing, breaking down thing. Yes, so that is where we're going to leave that process, because I couldn't find a slide with all the steps, so you don't have to memorize it. Good job. And that brings us away from the cellular components of blood. We'll go to the plasma, the watery components of blood. Well, we did the fibers with the fibrinogen just now. So, blood plasma, what we do with blood, we take a lot of blood, we put it in these centrifuge things where the vial of blood goes down and out a little. And then we spin it. And so when you spin, all the things that are heavy go to the bottom of the test tube, leaving the stuff that's not as heavy, which is the liquidy stuff, on top. And then when we take the plasma and we take away the clotting factor fibrinogen, well, the fibrinogen itself, then we have serum. Because when you need liquid blood stuff, you cannot have plasma laying around with all the fiber in it. The fiber will make it from insoluble to soluble and clot everything together. So in order to have plasma without it being a problem, you're going to have to take the fibrinogen out, and that is then known as serum. And here you got some vials with regular vial, normal blood. So it's about, 50-50, red and white stuff. But then you got anemia, not as many blood cells, so you got more white stuff, more plasma. Or we have too many red blood cells, polycythemia, we're going to have more red stuff, so it's unbalanced that way. What is in the plasma? Most of the plasma, 90%, is water. And then we got some dissolved substances, and most of them are proteins. 70% of them are proteins. When you look at what proteins do, well, proteins in the system are transporting for lipids. They create transport vehicle for lipids. That's your LDL, HDL, that kind of stuff. They help in the blood clotting. We just talked about that. They can be free-floating antibodies of the immune system. We briefly mentioned what that is so far. And then the other thing that the plasma proteins do is they create an osmotic pressure. And the biggest one that does that is the albumin. That's the most numerous of all of them. And remember in cell, the transport of water across the cell, across the membrane that only lets water go through but not solute, not salt, for example, the water will pass through. Remember when I told you about the tomato and the salt? You put the salt on the tomato, the water comes up, it's a little bit later, it's the salt droplets. That's the salt pulling water up. The movement of water through a medium, through a membrane, is called osmosis. So when I like go and take this blood from the heart with oxygen filled, and I go through the body tissues, and all the blood is going to seep into the tissues, the albumin will stay behind and create that pull that the fluid, after it's gone through all the tissues, fluid can be pulled back into the bloodstream. Because it seeped all out. How is it going to come back? It's pushed out because the heart's pumping it out. That's the hydrostatic pressure. That's water pressure that comes out of your hose. But once it's seeped into the tissues, how are you going to get all that thing back from the tissues into the bloodstream, that then you bring it back to the heart and to the lungs to get oxygen back and all that? That's these big molecules that are laying back in that liquid. They act like the salt. Albumin acts like the salt. It's going to pull that water out. It's not salt, but it acts like that, just to remember it. And then besides the proteins, we got other stuff. We got some nutrients, we got some vitamins, low molecular weight stuff. But most of it, proteins. Proteins, transport, lipoproteins. That's the next topic we're going to talk about here for a little moment. So we have a few more going here. So let's go a little bit deeper into the lipoproteins. So they transport lipids, which we talked about. That's the vinegar and the oil. So lipids are insoluble in a water environment. Again, water is hydrophilic or water loving. Lipids are the opposite. They're the oil. When we look at lipoproteins, we talk about a few classes. We talk about HDL, we talk about LDL. You heard about those? Cholesterol, you heard about cholesterol? That's cholesterol stuff. So we have some, the HDL, that we call good cholesterol, and they go through the body and they pick up lipids and they bring it to the liver for processing. None. So they're like vacuum cleaners. They call them the good cholesterol. But then we got the other one, the LDL or even the VLDL. LDL stands for low density lipoprotein. The V is for very low. The H is for high. So it's just how they feel, what goes on with them, that's how they're named. But the LDL and the VLDL carry lipids from the liver to the body. And that makes them more problematic. Because they distribute all the lipids that then the body gets and clogs all the arteries with. At least so we think. Now we know also what's really important in all of these problematic processes is inflammation, much more than fat. And so we gotta figure, because they did this margarine thing and they realized margarine didn't do nothing. And it was the inflammation went up because you got this linoleic acid, or they call these different things. There's higher in the trans fats and all that. So they had to learn that. But the good and bad cholesterol is still a player. We want to have it be in balance and not have the LDL be too high. We want the HDL be higher and the total be at a level.
So is that why your body likes the healthy fats, because it's easier for the liver to process?
You mean how you feel you like you feel your body likes them better versus getting lethargic kind of thing? Yeah, I think so.
We always hear about healthy fats, this, that, and other, but it would play into what we're kind of talking about now, right?
Well, yeah, in some ways it also plays in, especially when it gets to the trans fats, because it really sets up these fats. Fats are signaling molecules a lot of the times too. They're hormonal kind of things. So they tell the body what to do, and the trans fats really mess up that signaling thing. And I have a feeling, unfortunately, the plastics do a lot of that too. That it seems like we all have them in our tissues when they measure. But I've just put a few. I like this slide, the way it just sort of shows you all this, the round things or the polar things, and then the tails are the non-polar ends. They're like, triglyceride. The triglyceride. Remember that? All these carbon chains. Well, one of those carbon chains is just the polar end of it. So it's flipped it around, so it's like a phospholipid. So it's always the same thing. It's always like this phospholipid layer or phospholipid bilayer. And this, when you transport lipids around, you just need a phospholipid one layer, because on the inside you have hydrophobic already, and then the fat can travel with no problem, because it's in its own environment. Yeah, it's funny how that water-loving fluorine is such a fundamental such a fundamental thing in physiology and anatomy. Then the other protein we talked about, the antibodies, the immunoglobulins, and those are part of the specific immunity, because antibodies bind to specific antigens, tagging them, and then when they tag them, they call that opsonization, is the tagging process. And then sometimes they precipitate out because they all clump together at that point. And so what I did here is I found this nice chart. You don't have to memorize all that or read all that, but I found all the different classes, the 5 flavors of the immunoglobulins or antibodies. It's the same word. And so that's, they call them, one called IgG, AMED, gained. And then here's what they do specifically. I'm not gonna, they all do the same thing, but some of them are found in different body fluids, some of them are in mucous membranes, some of them are in the mother's milk, and so forth. So I just want you to have this part. It's a very helpful chart, but we don't have to go too crazy in all the details. It's just more confusion. One of the things, though, I really like that they can do when they have an invader that they recognize again, they have this membrane attack complex that can create, and they make a hole in another cell and destroy the cell that way. So they can directly also fairly well attack certain things. So that's nice. That's nice. That's nice. We'll talk more about that in the immune system. Then we get to the transportation. So of oxygen and carbon dioxide. That's our main one to talk about. So the hemoglobin transports the oxygen. Oxygen comes from the atmosphere. We breathe it in the lungs, into the alveoli, and from there it diffuses straight into the bloodstream, because when the blood, that's a tissue cell. When the blood travels by the alveoli, it's got such a low concentration of oxygen in the blood and such a high one in the alveoli that the oxygen just goes right in. It's like a magnet, it sucks it in. So diffusion, you think of a magnet just sucking it in. And then when we are in the tissues, the hemoglobin will let go of the oxygen and let the oxygen go into the tissues. So it binds to oxygen reversibly, wherever that's somewhere standing. You can pick it up or let it go. It's like a magnet. The strength of the magnet is the question. Then carbon dioxide is a bit more complicated. Most of it is bound chemically to soluble bicarbonate. We go back to the chemistry chapter. We talk about acids and bases. We talked about how the acids are too many hydrogen ions, and the bases are too many hydroxyl, the OH ions. Together they make water. But we got to be able to balance them out and pick them up when we need one balance to the other. Bicarbonate is that buffer that can do that. That's your Alka-Seltzer. That's, you've got upset stomach, the stomach acid, bicarbonate picks it up. And so it balances the pH. It also goes and binds carbon dioxide together. So carbonic anhydride is an ASE, so it's an enzyme, and that in the red blood cells, and that binds water with carbon dioxide, making bicarbonate ions and hydrogen ions. And so that process is right there happening. And so carbon dioxide is not moving on the hemoglobin, it's moving through the cell, through the body on bicarbonate ions, as bicarbonate ions. So that's the most important part here. And what's interesting also is that oxygen and carbon dioxide transport, they influence each other. So when we have deoxygenated hemoglobin that acts as a stronger base, then if it's oxygenated and therefore binds more to hydrogen ions. So which then is produced when we pick up, CO2, from the tissue. So we fostering that process. So not enough oxygen, more carbon dioxide can come in. So they balance each other out, and they work with each other. I'm not giving you a good job here the way I explain it. Just know there's many factors that influence these things. And for the most of the time, that assures that the tissues get adequate amount of oxygen. That's the main thing. So the more the tissues need the oxygen, the more they get the oxygen. And that brings me to the last topic. I hope that's the last topic. It's got to be the last topic. Blood groups. So when we do transfusion of blood, we have more than 100 different types of cell surface glycoproteins. So that's an antigen thing. You think an antigen. So on the surface of our cells, we have little indicators that tell this red blood cell belongs to me. If I give you this red blood cell, your red blood cells might not have these bumps, not have these antigens. We call them antigens, these little self-identifying markers on the red blood cell. And your body is going to react to it because it's got antibodies against it. So when you think of antigen, you think of antibody. So an antigen is usually a part of a pathogen that makes us sick and creates a reaction of our immune system. And then the immune system creates antibodies against it that it can fight that problem. With this, our cells have their own little antigens on them. But they're only antigens, so to speak, that cause a reaction if they go into a system that has antibodies for it. And so when we have a blood transfusion, we need to make sure that we don't mix up the wrong antigens with the wrong antibodies. Because if we do so, your bloods will all clump together and we die. It's so-called hemolysis. Look here, hemolysis. So, in us humans, we have two systems. We have the ABO system and we have the RA system. So in an ABO system, we basically have two antigens that we look at. We have an antigen A and we have an antigen B. When let's say I'm an antigen A and I got group A. So my body has, if I have A antigens on me, my body will have antibodies for the other one, for the B antigen. So if you give me type B blood, which has B antigens on it, it's going to cross-react with my antibodies because my antibodies are for that antigen. Clump together, bad idea. So we got to make sure, we got to take a little of my blood, a little bit of this blood, make sure it ain't clumping together. If it is, we got a problem. Now, some cells, some red blood cells have both antigens on them, A and B. Those bodies, those people, they don't have any antibodies against these that they have themselves. So they can actually get blood from either of these and there's no problem. They have nothing to react to. However, then we have these cells, they have nothing on them. There's these people that have no antigens on them. That's that O thing. The zero, it's a zero. And those have antibodies for A and for B. So they're screwed. All you can get is the blood with nothing on it if you have a transfusion. So this all became a problem when we started doing transfusions. So when we do this kit over there afterwards, hopefully, when we look at blood, we know our blood type is what our red blood's antigen is. That's the name of the blood. So if I have antigen A, my blood type is A. If my blood cells have antigen B, my blood cell is antigen B. My blood cell type is B. We don't go by what antibody you have. We go with what antigen is on your blood. So that the one person who's lucky actually with antigen A and B on their blood, they have no antibodies, they can get all the blood they want from everybody. They call that the universal recipient. Lucky. And then the one that has no antigens can give the blood to everybody, but cannot receive blood from anybody. So they call that the universal donor. The unlucky one that way. Although it's nice to donate.
That was antigen O.
Yes, but O means none.
Okay.
O means 0. So it's either you have antigens A or antigens B, both of them, or none of them.
So if you're group O, then you can't receive any blood? You need like a
Well, from the O people.
only from O though?
Mm.
And nothing from, okay.
Doesn't the RH factor play?
Yeah, let's go with the RH. The RH, I always have to read that. RH stands for rhesus monkey. It was discovered when guinea pigs were injected repeatedly with blood from rhesus monkeys and their blood coagulated or agglutinated. So people that have the RH antigen are known as RH positive. But unlike the ABO system, RH antibodies are formed only after the recipient is sensitized. That is, after the immune system has learned about the RH antigen and slowly makes antibodies against them. So if you're exposed once, no biggie. A first exposure does not cause rupture of the foreign RBCs, but a second one will. And by the way, again, that's exactly, again, the specific immunity, the learned immunity. We have to be exposed, the body learns about it, and then it makes these antibodies. So this is a problem when you have an Rh negative mother that gives labor to an Rh positive child, to remove some of the child's red blood cells spill over to the maternal blood, sensitizing it. In a second pregnancy then, to another Rh positive baby, the mom now has Rh antibodies that cross into the baby's blood, which will agglutinate the baby's RBCs. So the mom's first child, no problem. Mom's negative, baby's positive. First child, no problem. But during the pregnancy, it spill over a little bit. We got to make antibodies, second pregnancy problem. And that's where they give them Rogan. So that's not a problem. But that's the big deal about the RH. So when you have a system, and don't you like the footsies? I know, I saw it, I was like, that is so cute. I can't want to come out. So when you look at your blood thing, you have an AB, ABO, or O, and a plus or a negative. And the plus or negative stands for the RH. So with that in mind, why don't we go over there and just do that? And then we leave it at that for today. So in lab, what we're going to do is I want you to look at these blood things a little bit. I have a handout for that I'll be handing you out. And then we should do the blood kits. And I'll be handing yours out over there. And then we'll call it a day.